Hey, welcome to what I hope is a interesting series on creating a virtual console, a sort of a little virtual games machine using AI as an assistant, which is possibly a controversial topic for some, but let me go through why I think developers should be using AI. So why create this series? I've been using LLMs to support me in my coding activities for a little while. They've come on in leaps and bounds. The latest sort of tools are really useful and a massive force multiplier. So if you're a good developer, they will help you get a lot more done. If you're a really good developer, they'll let you get n times done. It's always n times. If you're a new developer, they can be somewhat challenging, which I'm not really going to cover in this guide. But maybe I will do a little side session on it. In any case, I think they're really important tools for developers to be using. They are not magic beans, they're not like magic solutions. Sam Altman, Satya Nadella and co, they love to hype this stuff up. The hype's almost to the detriment of the actual tools, I find. They are really useful, but they have limitations. And you really have to work with them, not have them work just autonomously for you. But we'll go through some of that in this series. So I think developers need to be using them. I think it's really important they get on board. And as to the ethics of them, so I understand why people have some ethical concerns about them. I have some ethical concerns about them. I don't think society is necessarily ready for the change that they could bring. There is a lot of potential for harm. You can see some of that already. Some of the Sora stuff that's been going on is terrible. I think some of these corporations are out of control, essentially. Governments not even trying to catch up in some cases. Some governments scrabbling to catch up. It's a real mess. But it's not the first mess in the tech world. It has a potential to perhaps be the worst. So that's kind of one side of it, the behaviours for companies, and then there's the training data that they've been given access to, which, I'm not a lawyer, but you can see from the way some of the court cases have gone that there is at least reasonable grounds to suggest that they have been trained in a way that would be considered illegal. You can see that in some of the settlements that have gone on. There was a famous case, I think, last month with Anthropic and the books, where they've agreed that they've essentially settled, I believe, a sort of financial amount which is going to get shared out. It's disgraceful. I think there is a difference between people, copyrighted works that were not kind of publicly licensed being used and publicly licensed works being used. So one of the things that some people have got a little bit upset about is, for example, training on public code, code that's on GitHub and co. Unfortunately, if you put things out for a public license, it's out for a permissible license. It's out for a permissible license. And yes, you couldn't predict that perhaps that AI would be trained on it. But you put it out for a permissive license. That's what you do when you use a license like that. You let the world decide what it does with it. So I think that's fine, training on public source code. That's fine. That's what people did. You can't cry about it after the fact. I think, obviously if it's been used on stolen source code, that's a completely different matter. So yes, it's all ethically dubious, murky, big tech as per usual, using their muscle to force things, deeply unpleasant. But I think the unfortunate reality is for developers is it's such a multiplier that if you're not on board with it, in a couple of years you're going to be struggling to put food on your table because you will be unproductive compared to people who've got on board with it. So I think, some people will choose to make an ethical stand, and that's laudable in many ways. They may find themselves out of work as a result. That's the price sometimes of making a stand like that. To me, I think people need to put bread on the table. I want to put bread on my table. I want to stay in a house. want to keep my dog well fed and looked after. And also, it's another tech transition, and you just need to get on board with it. So, ethics, yes, it's somewhat dubious. Sad reality is it's not going anywhere. You need to get on board with it. That's my view on it. If you're not happy with that view on it, obviously leave this video now. I think I've made it pretty clear in the title that this is going to be using AI. So with all that out of the way, let's dive into what we're going to be building and take a look. So I mentioned, so one other thing actually before we get started, expect some chaos and carnage in this video series. I have not built a virtual console before, and I am not kind of rehearsing these episodes. I'm just going to try and make something, which means some things are going to go wrong, and we'll have to figure them out on the fly. But that to me is part of the point of the series, is to show the reality of working with, an LLM. I will get some things wrong. I'll use the LLM wrong at times. I'll probably forget to review something at a point in time. I am only human. I'm currently recording this at 6:30 in the morning because I also have a day job and I need to fit this stuff around those things. So there will be mistakes, but I think that's part of the process. So expect some chaos and carnage. I'm not going to do massive edits of these things. I may snip out some time when we're waiting for things. But yeah, it's literally going to be live coding. I'm just recording it rather than streaming it. Mostly because I don't have an audience really, and also because I don't watch live streams. I tend to just find things on YouTube that I want to watch later. So this is a bit, in many ways, more of that. In any case, let's dive into what we're building. I've mentioned it a few times, a virtual console. I grew up with the 8-bits. I was more on the computer side than the console side. My first computer was a Dragon 32, which I think I had for about a year. And then I got a BBC Model B, probably been a few months of those things being released, so I guess 82, 83. It was super exciting. I learned to code. I started with BBC Basic. I think I was in 6 or 7, something like that. I started BBC Basic and eventually, like most people, started to tinker with assembly with 6502, which is the CPU that was in the BBC. Obviously, the consoles weren't particularly big in the UK, as I recall at the time. It was only later with like the SNES and the Mega Drive that they really came to the fore, at least in my sort of sphere. But obviously, I'm into my old games and I look back on that era fondly. And I kind of wanted to create I won't call it a dream console, but what were the pain points I had on the BBC? How might I fix them if I wanted to make games? And that's what this is about, a virtual console. So it's somewhat 6502 inspired in terms of the CPU, and I've spec'd out a CPU, which we'll talk about in this episode. It's got a RISC twist on it. It's not completely 6502 because 6502 was wonderful at the time, but also in many ways a little bit painful to work with. You only had 3 registers, A, X and Y. You could think of those as having, if you've not done the assembly language, you could think of those as having only 3 variables that you could ever use, A, X and Y, and only one of those variables could you do arithmetic on. So you were always shuffling things between those 3 variables, loading things in and out of memory. And it also had no built-in multiplication or division, so you had to write your own, which wasn't a great drama, but it's just an indication of how simpler CPU it was, simpler chip it was. It was very cheap and really quite powerful for the time, for its price, I guess. So it found its way into a lot of systems. In any case. We're basing this on a 6502 thinking with a RISC twist, and we'll have a quick look at that in this episode. It's going to run at 3 megahertz. My 6502, my BBC, ran at 2 megahertz for memory, so this should be a bit quicker. And I think the way we've structured the opcode means it'll be quicker still. And the fact that we don't have to move things out of registers all the time will hopefully make it quicker still. So we'll spend less time shuffling things in and out of the 3 variables. We're going to support, I think, 4 screen modes. I've documented that in the video markdown, which we'll talk about when we get to that point. But basically, an 8-bit per pixel mode, and I think two 8-bit per pixel modes, so that's 256 colours, and 2 4-bit per pixel mode, which is 16 colours. And we're going to give access to the video RAM as like a linear space in memory, which means you can adjust individual pixels. That's all you could do on the BBC. Obviously, things like the Commodore 64 and the consoles had hardware sprites. The BBC, you had to literally code those sprites yourself, as it were, by poking bytes into the video RAM. We are also going to have hardware sprites on this system, and we're going to have tile maps. So let you lay out levels of tiles and hardware power all that. And that's the kind of console end of it. That the BBC was not a games console. It was a machine really for learning how to code. That's how I saw it anyway. This is definitely aimed at games. It's got some additional hardware features. We're going to build in collision detection. I think the C64 might have done that, but I could be wrong. I'm pretty sure one of the early machines did. Maybe the 2600, the VCS 2600 too. Anywho, we're going to build in collision detection, and we're going to have multi-channel audio, which I have had to research because I really don't know much about audio. I've spent lots of time with graphics and GPUs and very little time with audio. Despite the guitar in the background, I have little audio talent. So that will definitely be a learning journey. Pardon me. Yes, and one other thing on the CPU before we dive into it. It's a long time since I did any serious assembly. So I'm coming at this project pretty uninformed, I guess. I've certainly never tried to sort of build an emulator at any level, as I recall. As far as I did have a bash at a 6502 emulator. Might be my GitHub. I didn't really get very far with it. I was just playing around. So it's a fairly new to me. There's lots of stuff here that's fairly new to me in terms of emulating an 8-bit, simulating an 8-bit. So it'll be quite, I'm coming at this fairly cold, which I thought would be a good way to use the AI rather than come at it as something I already knew, come at it cold. We're going to implement it in TypeScript. So it's going to present in a web browser, and the idea is we'll have a sort of a public-facing website that you can pick carts or drop carts onto the console and it'll run them. We're going to have a dev kit website, so we'll surround the console with some developer tools, an editor, an assembler, and we'll come back to what an assembler is as we get into the project. I figured that might be interesting to build the dev kit around it, some basic tools for graphics. Make it hopefully fairly straightforward to create a game for the console. I'm toying with the idea of doing a BBC Basic compiler as well. It's long been a sort of dream to write my own implementation of BBC Basic. I don't know what. Well, I guess nostalgia. I grew up with it, and it'd be great to sort of create my own version. And I figure it might be fun to write a compiler for this. So that would be a part 2 perhaps, but we'll see what we get to. So in this repository, and I'll share the link below the YouTube video, it will have a CPU implementation, and hopefully by the time we've done. But in this repository, there's basically a few folders which I've pre-created. There's a specs folder, and under there I've got hardware, implementation and tools. Let's expand tools so you can see that folder. I basically started to lay out what the console should be in the specs and what the system should be in the tools. So the hardware, I've spent a bit of time on what the CPU should be, a little bit of time on the memory layout. The interesting thing about the sort of 8-bit era was that the memory layout was the hardware, was very much for hardware. You would access the hardware through, setting bytes and reading bytes in the memory map. So in the 64K we've got access to, 8-bit system. There are bytes for the video RAM. There are bytes to do bank switching, which we'll come to, for setting up sprites, for audio, changing the frequency as a register, as a memory register, an area of memory. So the sort of hardware was exposed through the memory, which was very different to where we are today, 10,000 levels of abstraction away. It's one of the appeals of the 8-bits. They were really raw. The implementation folder, that's my notes, which I'm going to feed to the AI, and then I'll sort of supplement them with guidance as we see what it does. tools, I've only written something about assembler so far. This is what, well, I'm going to come back to this later. That's the, for assembly, well, I'll come back to assembly later. And finally, I've written a TypeScript guide. This is something I had a sort of, I had some of this, and then I kind of annotated it. Again, I used Claude, an AI, to annotate this and build it out further. And I tested it with a few things, a few generations, to see if it was broadly where I wanted it to be. There were a few things I found missing as a result of the test. I added them, I tested it again. But having a guide, a style guide, is really important, because otherwise the LLM will just have free reign. And what you get would be based on whatever code was kind of similar, I guess, in its training data that it had seen in the past. These things are predictive machines, they don't know. And a really stark example of this I found was using AI with C#. I write, amongst other things, sort of C# for a living, and I do it in a sort of enterprise space, a software as a service system, and it produces code that looks like code in that system. You're writing ASP.NET APIs, it's seen lots of that, it's trained on that. It produces what I would class as reasonable quality C# code. I then used it on a Unity project, C# with Unity, and it produced code that, to my SAS eyes, was absolute garbage, despite it still being C#. It was using reflection rather than making things public, and just doing really strange things. And I think it's because the Unity space has a lot of learners in it, a lot of beginners, and a lot of the focus is on just making things work. But it shows it has no inherent sense of what good C# is. It's just, kind of context and based and predictive. So it's really important to have a style guide. And we can talk about what good style is. I'm not going to talk about what good style is in this video, because we could take forever on that. And it's a different topic really, but you should have a style guide telling you what you think good quality code is. Finally, in the source folder, I've just created some placeholders, a couple of React projects using Vite. I'm never sure how you say that, V-I-T-E, Vite, Vita, whatever. Using that tool to create some basic websites. I've not run them yet, don't really care. And finally, I've created a console, which is where all our sort of hardware TypeScript is going to go. And I want the console to be independent of the browser. It should be able to stand up in Node. We should be able to run tests against it. So everything that goes in console should be fairly clean TypeScript, shall we say. Not DOM aware and not Node aware either. It should be pretty generic. We'll see how that goes. So we're going to tackle, just to keep kind of this thing manageable in terms of length, as a first episode, we're going to try and generate the CPU and have a first pass through the code. That's what we're going to do in this first episode with all my preamble out of the way. So I've written a spec on the CPU. I wrote it at the weekend. I was on holiday, but I was I couldn't get it out of my head. Really, once I decided to do this, like many developers, somewhat obsessive, I guess. But I did still enjoy my holiday. We did lots of hiking. We being me and my dog. So I generated this at the weekend. As I say, it's somewhat 6.502 inspired, but it has quite a few twists to make it more pleasant to use. Very specifically, it has 8 registers and 5 general purpose registers and 3 sort of special registers, which I'll come to in a minute. The 6502 has 3 general purpose registers, and only one of those you could do arithmetic on, which is the accumulator. We've got 5 general purpose registers that you can use for all purposes. And that should make things a lot easier in terms of coding, because you spend a lot of time on 6502 shifting things in and out of registers. We should have to do less of that. And I'm hoping we have, because by doing this, and I'll come to this later, I've kind of made an interesting decision around the amount of space that code takes up, but we'll come to that later. We've then some special registers. Actually, I should have put this up a bit. Anyway, sorry, there's 3 special registers. Just for formatting this document's a bit strange, I've realised just now. We've got a stack pointer. You can push and pop onto the stack. You can point the stack anywhere, really. there's some conventions for 8 bits. We'll see what we decide, and we start to do more work on the memory side of things. A program counter. So a program counter tells the CPU what instruction it's looking at and where to pull things from, basically where to pull data from. When you fetch an instruction, it'll be moved on to the next byte. That's a program counter, and then you've got status flags, which is another register, status flag register. And this was essentially, this is what's basically used to do your Boolean logic, your conditional logic, your branching. It was, it's not exactly elegant pattern matched switch statements like we use today. A lot more raw. However, at the moment we've got 4 flags inside here. Negative. So negative gets set if bit 7 gets set to 1 of any operation. That would indicate a negative value if we're interested in negative values. Going through this, I'm assuming people know what bits and bytes are. If they don't, go and look. Being of my age, of my era, there's some stuff I might assume, and I'm sorry if I do. Please do go and look if I do assume something that you're not sure of. So that's negative. Overflow is if you add 2 numbers together, for example, and you exceed 255. You've got 8 bits, 0 to 255. If you add 80 to 200, that can't be stored in a byte anymore. So you get this bit set. You get that flag set to indicate that you've overflowed on the arithmetic, and then you can handle it if you're interested in that overflow. 0 set if a result in operation is 0. Carry. Carry is similar to overflow. I get confused by these myself sometimes. It's a long time since I've used them. A very long time. So this is also used for arithmetic. It's a bit more broad, and again, it's if things kind of push out of the range, but it's a bit more opcodes are involved in it. And we'll come back to that later. And when I start writing some assembler with this, I'm probably going to have to revisit the detail of these things because it is a long time ago. In any case, that's the status flags. As I say, this is raw, and I'll be learning as I go too, because I have to relearn some of this stuff. Addressing modes. There are a variety of ways you can essentially pull data into registers or store things back into memory. And this was done through addressing modes. And the 6502 had some of these and not one of them. Immediate is just loading a value straight in. Register direct, just working on the 2 registers that you have. Absolute, here's a memory location, go and do something with it. 0 page indirect is where it gets a bit spicy. So the 0 page is the first 256 bytes of RAM rather. I always forget the 0 to 255. I forget the 0. But that first block of memory, you could use that essentially as a pointer to another 16-bit address. So if you wanted to kind of do things dynamically, you could calculate pointers, pop them in the 0 page, and use them as a pointer to an address elsewhere in memory. Indexed 0 page index is similar, but you can use a pointer plus an offset to go from that location plus 0, plus 1, plus 2, plus 3. Register pair indirect. The 6502 did not have this concept, but I think the Z80 did, which was used in the Spectrum amongst others. And in this mode, you can essentially have the 16-bit address in 2 registers and use it that way. So that's an additional mode we've got for address indirection. I'm not going to go through all the instructions in this. We'll sort of go through those as we start to write some code later on. and probably find the problems in them at the same time, because there will be problems, I'm sure. Let's scroll down to this one thing I want to talk about, which is the instruction encoding. So this is, you have to take all those opcodes, all those instructions, and represent them in memory somehow. And obviously we've got the opcode itself, we've got the addressing mode, and we've got the registers, or the source and destination. Might be register, that the destination might be register, it might be memory location, etc. Engage brain, James. It's early, forgive me. We need to represent that in memory somehow, and we're doing that through 2 bytes, which are formed up like that. So four bits of the opcode, 3 bits of the mode, and then 3 bits of the destination, 3 bits of the source. You can see how they map out here. And some unused bits. Now, I mentioned earlier that I've made a sort of interesting decision here. The 6502 managed to do all that in 1 byte, and that's because it had fewer registers. It had these 3 registers, so if you load something into the accumulator, that was LDA, on the 6502 that would be an opcode. Loading something into the X register would be LDX, and that would be another opcode. But we can't do that because we've got 5 registers, 8 registers in fact, but we've got a lot more registers, and we'll run out of opcodes. We'll run out of 255. We'll run out of codes eventually. So I have taken a decision that I want more registers. I think that'll make it easy to work with, and what I'm hoping is by having more registers, there's less code needed because we're not spending as much time moving things between bytes, and that will compensate for us using 2 bytes to store every instruction. Now, I suspect I'm still going to use slightly more memory than the 1 byte model with fewer registers, but we'll see if that becomes problematic as we get into things. But also, I've got a lot of bank switching and other things that we can do with the system that hopefully take some of the memory pressure off a little bit. We will see. So that was an interesting kind of decision I made, but I really wanted an easier register model. The idea of this is that it's relatively straightforward to work with and straightforward to compile to and things like that. I don't, although I want it to be an 8-bit system, I want it to be fun to build and relatively straightforward to work with. So that's the CPU spec. How did I create the spec? Some of it was by hand. Some of it I used Claude to fill in the blanks. I kind of wish I captured some of that, but there was a lot of back and forth between me and the LM. It was probably not that interesting. Maybe it is. I don't know. It didn't feel particularly interesting, and I was also on holiday in a Wi-Fi constrained location, and my curiosity was piqued, so I decided I would write the specs up front, and then we could work from the specs and talk through the specs. So again, I used AI to back and forth around some of this, particularly because my memory of it is quite distant. I also consulted my BBC Advanced User Guide, which I've got in PDF form, and I don't know if it's on the shelf behind me or if it's downstairs. That'll be on the shelf behind me there. I consulted a PDF version of that to refresh my memory on 6502 and look at how the BBC hardware was arranged. So that's how I put this spec together. I say there's probably some mistakes in it, and hopefully we will catch them as we go through the system. So we're going to look at now creating a CPU, and to do that I've created a very brief spec in here. I've just realised I renamed that to readme.md, so let's save that. And this is what I'm going to ask Claude to do. I'm going to ask it to read these files, the style guide, the README file, the style guide, and then CPU spec, and then I wanted to proceed with the CPU implementation. I want it creating as a class. I want the class to be in a file at a certain place. And then I've also noted that we need a way of connecting the CPU to memory. Obviously the CPU pulls things from memory, and that will be done through a memory bus. So we're going to create a class that simulates that and put it next to the CPU in our source code. that's what I'm going to give. That's what I'm going to give Claude. I keep mentioning Claude. I'm going to use Claude Code for this. So I've found basically. Let's just see, make sure I'm in the right place. I am. Let's give it. Let's just start it up. You can give it files at the command line as well. So I've found Claude Code to be, of all the AI tools on the market at the moment, to be the best one for generating things that are of significant size. So the best kind of agentic coding assistant. I've tried Copilot. I've tried Cursor. I have used JetBrains AI with various models. They've all got their pros and cons. But for generating significant amounts of code, I've definitely found Claude Code to be the best. I've also found it to be the best at interpreting large code bases. And it's using Sonnet 4.5, which some of the other tools are using too. So why might Claude Code be better? Essentially, these things are built, there's two things that really power the quality of the outputs of these things. One is the model itself. The other thing is called tools. So you connect the LLM to, say, what are called tools. Tools can also include additional AI capabilities, but what tools do are specific tasks. So find a method called X, get me this source code, do this, do that. And I think what Anthropic have probably done is spent a lot of time on the tools and got them to be the best tools. So Sonnet's a pretty good LLM for coding in the first place. Pair it with the best tools, you end up with the best solution. But it's an arms race, essentially, between these people. They're all competing to be the AI coding assistant. So it's possible that midway through this we change, we swap to a different one, depending on what's happening around us. We'll see, but hopefully stick with Claude so we're not jumping down too much. I will say I tend to use this in the terminal. I will use the sort of chat mode inside an IDE to do small updates and changes. So I hop between the two solutions. And sometimes I'll load up a different model. So I might go over to ChatGPT or something else if I find I'm not getting anywhere with a specific solution. We don't have to use just one system. We can use whatever systems we like. But let's ask Claude to implement our CPU impl. Please, I'm always so polite to this system. Oh dear, oh dear. Well, if the AI takes over, we want to be known as a good guy. Even if probably that please burnt off a bunch of energy. So I'm asking to read the implementation plan at spec/implementation/cpu-impl.md and execute it. And hopefully I've got the file path right and it finds it. Okay, so it's reading the spec. So it's chundering away, it's read some more stuff. It's read things in the order I asked it to, which is good. These tools are not deterministic, which is part of the sort of issue, as it were, with using them. I could run this thing twice, and it might do slightly different things. And part of we'll end up doing some of this. Part of working with these systems is getting your prompts and your specs into the right place so that you get the output you want. You kind of, not in many ways. I hate to. I can never say this word. I hate to anthropomorphize these systems, but it's not dissimilar to a person. If you give a person a vague requirement, they'll wander around and produce something that meets your requirement, but your requirement was too vague. It's not that dissimilar. So it's creating a memory bus class. What I'm going to do in this session, the way I tend to work with the code generation is rather than review it as it goes, I make sure my code is committed before I set off a big job, and then I will go through the change it's made after it's done. So I'm going to let it do all the edits it wants in the session because we've got a baseline. We can undo it really easily. But we'll watch it. If these things can take a little while, sometimes, and if I run out of things to say, I'll cut a bit out in the edit, but hopefully not. We'll let it chunder on. I'll add as well, I'm using the one of the max plans on Claude. If you look at their plans, there's a few plans. I found with the sort of standard plan, I think it's whatever it is, the $30 a month, $20 a month plan, whatever it is, if I use it for a day, I run out of, or use it intensively even for a couple of hours on big code, I run out of credits essentially. So I'm running this on a max plan, on the plan that gives 5 times as many credits, and there's one that gives 20 times as many. I've not exceeded the 5 times yet. I say yet. I may well at some point, but hopefully not in this project. It shouldn't be too big. Just why it's doing this, an observation I've had with using these tools is they lend themselves to systems that are really decomposed into small parts. The more, let's just see what it's doing. Okay, it's going to compile it to check it works. Let's let it do that. It's not found TSC. Probably go for a different tool. What's it called? I forget what the tool is. Anyway, let it go. I found they work well on things that are decomposed, because if things are decomposed into things with clear contractual boundaries, just review that. That's fine. I'm just going to let it do things that it can do. It's checking for errors basically now. It's written the code and it's looking for problems in the code. It's compiling it and looking for errors. If things have got clear contractual boundaries around them and they're small, that really constrains what the LLM can do and work within, and that massively improves their effectiveness. And I'm kind of curious as to where that leads us from a sort of architectural pattern point of view. I'm using it at the moment on I hate the phrase microservice, but on a platform that's really broken down in terms of its services. Let's just call it a microservice architecture. And it's working really effectively because all the services are small and I can constrain what it does, and there's a really clear contract. So that's working really well. It's done, which is great. Okay, so what has it done? Create a memory bus class. Okay, it's used a uint8 array. I didn't ask it to, but that's a great choice, and that's what we wanted. I should have specified that really, but it's drawn on its training data and come to a sensible conclusion. It's built as our CPU, looks like it's correct. Okay, let's have a look at the code. I often use WebStorm. I'm just using VS Code for a minute. I'm not entirely sure why, to be honest. I think because I was planning on using a Markdown preview, which I didn't use, but that's okay. But I might swap onto WebStorm at some point. I might keep using VS Code. I'm not as familiar as VS Code for kind of refactoring things, so we'll see where we get to. But it's created as a memory bus and a CPU. Let's start with memory bus. Okay, 64K address space. It's used the uint8 array. That's what we wanted. Generates a new uint8 array. It's got things to read and write bytes, and that was right. Low, high, yes. Okay, pretty simple class, and looks okay. That's roughly what I'd hoped for. I hadn't specified this, and I find one of the knacks, as it were, to using these things is knowing when to specify heavily and when to not. If you specify heavily, you always get something more in line with what you want, or you're more likely to get something in line with what you want, but you're going to spend more time on the spec. And sometimes you kind of get a sense that, it's going to be okay if you leave it some room. And in this case, it was okay with some room. So let's look at the CPU, which should be a lot bigger. Okay, we've got some opcodes. We'll probably at some point move those out into different types. I think our assembler will use them, but this is okay for now. Addressing low constants, okay. Batch condition constants, okay. Branch file condition, status file constants, okay. We can just quickly check against our status flags. Let's get the files open so we can swap around easily. 1076. Yeah, that looks right. Okay. Okay, then we've got our class. Okay, registers. Okay, again use a uint array. Good choice. We want these to be fixed size. Special registers, cycles. Okay. Get register. Set register. Reset. Set program count to get status. Okay. Should be a step. Okay, so I was looking for something like this. So this is what's going to get it to kind of execute an instruction. So we're going to start cycles. I'll come back to at a future point, but they have to do with how long the CPU took to execute this instruction, basically. So it's about timing. It's not that big a deal in our emulator. Well, actually, it might become a deal because I've got some ideas for scanline interrupts, which I've put in the spec on memory layout, which we'll come to in a future part. So timing would become important there potentially. But cycles are everything when you're coding on the 8 bits. You spend a lot of time trying to reduce the number of cycles that something took to run, because that would make it quicker. So if you're trying to move, like on BBC, for example, I said it didn't have hardware sprites. So when I was writing a game in 6502, one of the first things I had to write was something that could move a sprite around the screen in code, sort of manually. And if you're moving, say, 4 sprites or 5 sprites, the performance of that became really critical. Even moving a small image was a challenge, for back on these machines. So you would essentially find cunning ways to reduce the cycle count. And I don't think I was ever a particularly good assembly programmer, but the great assembly programmers would find incredibly cunning ways to do things that reduce cycle counts with little tricks and things. And if you are interested in that kind of thing, there's a chap called, and I hope I get his name right, Mark Moxon. Let me quickly find him, because it's a really great article. Let me just find this. If you're interested in assembly, it's Mark something. Well, here's the site. Can't quite see his name on it, but here's the site. Let me just pull it back over. So this is well worth reading. This guy, I can't remember his name. I'm pretty sure it's Mark Moxon. I was right. Okay, Mark Moxon. He's basically gone through a bunch of classic BBC games and an Archimedes game, which was a 32-bit computer, and decompiled the assembly and documented it all. And he's created a bunch of long-form articles about how and why it worked and the tricks that were used. And one of the things he's done is document Elite, which is the famous 3D game. So this is a 3D game running on a 2 megahertz 6502 CPU in 32K of RAM, and most of that RAM had gone to the video memory. So like an amazing achievement, and he's documented how all this works, and like how a 3D map is implemented. It's incredible. Like, it's so cunning. It's amazing. So if you want to learn a bit about assembly and the kind of crazy stuff you would do to get it working on the 8 bits, this is a great fun way of looking at it. He'll go through the code. It's all annotated, how it's working, how the algorithms translate into assembly. You can go and look in the code. Highly recommend it. They are brilliant. But cycle counts is a really important part of that. I tend to get sidetracked by things that interest me. Anybody who knows me is used to this. And then executing instruction, okay, pretty normal. Let's look at a basic execute of a load. Okay, so immediate mode, fetch the byte, put it into the value. Yeah, great. So this is going to read the value based on the addressing mode. Okay. Okay, so one thing I've just noticed I don't like these constants being shortened with acronyms. There's no real need for that. So I might update my style guide, and we'll see if we can get the LLM to tweak that in a minute. But this is basically using the addressing mode. It's pulled out resolve address because that can be used for every addressing mode all over the place. It's reading the value based on the addressing mode, and then it's setting the value in the register, and then it's going to update the 0 and negative flags based on that. You can't have an an arithmetic error when you're just loading a value, but loading it, you might have loaded a 0 in, and you might have loaded a negative value in. So you might want to branch based on that. Branching is like if-then type constructs, if-then else. If it's 0, branch. If it's negative, branch. And branch is just moving to a different point in the memory space, so you can keep executing the program. Great. Okay. So I'm not going to go through all this now because this is already quite a long video. But when we come back in the next part, what I'm going to do is generate a test suite for this, and we'll have a good look at the test suite. But before I kind of move off, I'm just going to see if it can update the addressing mode constant. This is the sort of thing you could do manually, but you could also ask the AI to do. Can you update the addressing mode constants so they don't use acronyms and are more readable by a human? I'll see what it does. And yes, it would probably be quicker for me to go in and do it, a tool, but I want to demonstrate how you can use the LLMs. Yeah, that's better already, right? I can make more sense of that than mode, RP, and things like that. You can see it's going through, updating the rest of the code. Checks it compiles, it doesn't compile, look, it's missed some things. Yeah, it created some crazy constant names. Okay, let's look at our source code. Yeah, okay, that is better. I can understand this now. The opcode you kind of can't get away. That's what the opcodes are. And when we start writing assembly, we'll be writing nop, lud, st. That's literally what we're writing. So they're fine. Extended opcodes, by the way, are ones that don't require modes and things like that. So they can be stored a lot more simply and handled a lot more simply. That's the difference between kind of extended instructions and normal opcodes. Yeah, so I think I'm going to leave it there for this first episode. In the next episode, we'll write some tests and perhaps see if we can run some code and get some kind of console output as well. So we'll create a little assembly program. Even we don't have an assembler. Assembler is what takes the LUDs, the strs, and converts it into the bytes that actually this thing compiles. It does compile down to the bytes. We don't have an assembler yet, so we'll have to kind of do it by hand. And I don't fancy doing it by hand, so I'll probably try and get the AI to do it for me, and I suspect it will do that absolutely fine. But we'll see. So yeah, that's the start. I hope this is, I don't know, an interesting topic. I'm gonna try and do these. I'm gonna try and do these at least weekly. I do have a day job. I'm very busy in my day job, so I'll see how I get on with this. But I'll try and do them weekly. I've long wanted to make a virtual console, so it's a really interesting project for me. We will see how it goes. With that, thanks for watching. Hope it's interesting, and see you next time.